Hello, there's exercise 12D for year 12 for the normal math, sorry. And we're going to look at some vector problems today. And these probably are most like the type of vector problems you saw at GCSE. So I'm hoping you find these okay, but I suppose it depends how much work you did on this at GCSE. So a few things to remind you about. This rule I'm going to show you now is very much like the rule that we see in coordinate geometry. And if you remember, the rule says if you've got a point A equal to, I don't know, 2, 3, and you've got another point B equals, I'm going to make up a point 9, 11, and I want to know the halfway point between them. Usually we call that M, the midpoint of the 2 points. I mean, you might even write it like this. And the rule basically says you go 2 plus 9 is 11. Well, half of that is 5.5, or you could just write 11 over 2. And 3 and 11 is 14, half of that is 7. And it's the quick and easy way of finding the midpoint of two coordinates. Now, there's an equivalent method of this with vectors. And this is the logic. If I want to go from, find the midpoint here of M, and it's the midpoint of, obviously, halfway between A and B. The logic is to get from O to M directly. Ooh, wasn't my straight route, but you get the idea. To go from O to M, I could think of it as going from O to A and then from A to M. And for that reason, if we just essentially know what half of this is, I suppose that's the problem. A to M, we've got to go halfway from A to B. Now A to B, we've seen before, is quoted as B minus A. Therefore, AM is half of that distance. Notice it's simply written as half of B minus A. And we, therefore, to go from O to M, I'm going to write this here, O to M. Well, as I say, I think the way to go from O to M is to go up to A, which is A, plus this AM going across, which we now know is a half of B minus A. And if we just multiply out those brackets, you get you get an A plus a half of B minus a half of A, which is great because what it means is A minus half of A is actually half of A plus half of B, or put a different way, half of A plus B. Now that reminds me very much of this rule. The rule said take your X values, add them and half them. Take your Y values, add them and half them. And I look at that and think, you know what, it's the same rule. And that's our rule. M equals a half of A plus B. An example then of this would be position vectors 3, minus 5 for OA. I'm going to try and draw this fairly accurately. If I put that as my origin, then O to A goes 3 across, 5 down. There's my A. I'm hoping I don't regret putting them there. OB says it's 4 across and 2 up, so a little bit further. And there's B. Where does C? It's minus 3, minus 1, so C actually goes a little bit. But C's about there-ish. I'm not exactly sure where. So I've got my points O, A, B, and C. Find the position vector of D such that A, B, all right, A, B, C, D. Oh, I wish I had drawn it more accurately. I reckon it's got to be down there somewhere. Don't know what you think. There. Notice I went round in the right order. A, B, C, D. And by that definition, I think A to B, for instance, has got to be the same as from D to C, or I could go the other way if I wanted to. I can go from B to A. It's got to be the same as C to D. And that might be useful, actually, if I do it that way. It wants me to find this position vector of D. Let's find BA first. Now, the way I've written that, you always change the order. It's A minus B. And A is 3 minus 5. Minus the B, which is 4, 2. So 3 take away 4 is minus 1. Minus 5 minus a 2 is minus 7. So that's the vector. It goes 1 left and 7 down. It actually looks quite like that. Now to work out what the position vector of D is then, I reckon the position vector OD, you start at C and go down that vector. So one way of saying this, again, it's the same as just now when I showed you that picture. One way of going from O to D is to go directly, or you could go directly to C and then go down. So I reckon O to D is the same as O to C, followed by C to D. And you'll notice the middle letters agree, and that's why it's the same. And so O to C, what is it? Well, O to C, they've told us in the question, it's -3, -1. C to D, I've just calculated. Well, I haven't, but BA is parallel to CD. So I think I can write over here that CD is also equal to -1, -7. So I can write a -1, -7 here. So that's -3 plus a -1. I reckon that's 4 left. And -1, -8. That's what I reckon the coordinates. Does it ask? No, what's a position vector? So the position vector of D, I think, is this. M is the midpoint of AC. Where's AC? Oh, right. So that vector there, in the middle of it, we've got an M. Find the position vector of M. Well, the great thing about finding the midpoint of two vectors is we saw what you do just now. This is equal to a half of. Now, because it's the midpoint of A and C, it's the half of A plus C. So let's do that. It's a half of, what was A? A was 3 minus 5, plus C was -3 minus 1. Which sounds like a half of 3 plus a -3 is 0. -5 plus a -1 is -6. And I reckon, therefore, it's 0 -3. That's my position vector. And show that M is also the midpoint of BD. Now, BD, of course, goes the other way around. Well, I suppose we do a similar trick, I suppose. We do the midpoint of BD equals, I suppose technically I should have written AC for that one, but it doesn't really matter. MBD here, the midpoint of BD is a half of B plus D. I suppose it assumes that I've got my last D coordinate right, vector right. So it's a half of B. What was B? It was 4, 2. So that square bracket as well. Plus, what was D? D was -4, -8. -4, -8. It sounds like a half of, what is it? Top line is 0. That's good. 2, that's -6. Well, I think that's the same answer then. That's good. 0 to -3. I think it's worked. Have I got answers for this? Yes, midpoint is 0 to -3 as well. And OD must be right because we got the rest right. So I'll like that. Okay, yeah. Next example. Use the parallel vectors and A, B, and B, C to determine whether these points are collinear. Well, right. Now look, if 3 points A, B, and C are collinear, I should point this out to you. If 3 points A, B, and C are collinear, let's write them down. A, B, and C. That basically means they're in a straight line. It means I can draw a straight line through them and it hits all three. Now, the consequence of that is that line there is parallel to that line there. And that might be the best way to do it. Find AB, find BC, and then show that they're the same thing. So I've got one here with numbers. So let's do A first. So if I do A, I'm going to first of all find from A to B. So AB, remember you will switch letters, it's B minus A, which equals -1, treat that like a vector, -3, 2, and therefore -1, -3 is -4, and -2. Do the same thing for the other vector from B to C. B to C equals, now this will be C minus B, which is 11, 6, minus -1, 0, and that equals, what's that, 11 minus, that's 12, 6, 0 is 6. Now on the face of it, they're not the same, but they don't have to be the same, they have to be parallel. So can I write, this is what you've got to ask yourself, can I write I'm going to write BC actually as a multiple of the other one. And if I times that by minus 3, I get 12. And if I times that by minus 3, yes, BC is minus 3 times by AB. Therefore, they are parallel. Now, the basic idea of this is because they share a common point, they share a common point B, share B, therefore collinear. Because I suppose they could have been, we could have had a vector there which was parallel to a one over here. That doesn't mean they're all in a straight line, it just means they're parallel. It's because they all go through B. AB goes through B, BC goes through B. Therefore, they must be not only parallel, but in a straight line. Therefore, they're collinear. Let's try B. Should be exactly the same, really. Let's do AB first of all. AB, well, I'm going to do 7, take away 2. Well, it's 7, 7, take away 2, 5, I suppose, technically. And that equals 7, that's 5, 2. Let's do BC the same way. BC is minus 10, 1, take away 7, 7. Minus 10 minus 7 is minus 17. 1 take away 7 is minus 6. Now, I don't think these are collinear. Look, could I times 5 by something to get 17? Yeah, I can. It's not very nice. It's actually minus 3.4 to get minus 17. But if I times 2 by minus 3.4, I'd get minus 6.8, which is not that. So I'm going to write not parallel as AB is not equal to some sort of letter K times BC. Therefore, not collinear. The question says, are they collinear? Well, I suppose we've just proven they're not collinear. C. Are these collinear? Look, on the face of this is much harder because it is algebra. But let's just do it the same way. AB. Let's do AB. I've got to do this vector, take away this vector. So I shall do a squared 3a minus a squared minus a and 5a. Now I think a lot of stuff cancels out there. A squared minus a squared is, well, that disappears, but I've got a minus a. And 3a minus 5a, I think that's minus 8a. Well, I've got one vector. We'll soon find out if it's collinear, I suppose. BC equals a squared plus 5a. A squared plus 5a. Notice I'm doing C first. And I take away the B. What's it? So it's a squared and 3a. So easy. What's it? The a squareds cancel again. I think I get 5a there. 7a minus 3a I think is 4a. They don't look collinear to me. They don't look collinear because what would I'd have to times the a by the minus a by minus 5 to get 5a. But if I times this one by the same number, I get 20a, or minus 20a. So again, I don't think these are collinear. AB is not equal to some value k equal times by BC, therefore not parallel. I was expecting them to be parallel, I must admit. So I'm then going to say not collinear. Yeah, I mean, in my mind I was thinking those bound to be. Let's see what my answers are. Yes, no, no. So I got them right. Got one more question. We'll do this in class. This is the type of what I meant is very much like GCSE. But we haven't got time to do it now. But we'll save that for class. That's no problem. And in class we will have a look at exercise 12D and hopefully make some good progress on that. So all the best.